Those of you that are particularly observant may notice, hey, Mr. Dewick, it says lesson 5. Actually, in the curriculum, energy and momentum are part of one big unit. And we did 4 lessons last unit. I split them up into 2 smaller tests. Each test is worth 6% overall, because I thought it was a lot to cover all at once. However, there are some really nerdily cool questions that combine both energy and momentum. We'll be looking at some of those. So lesson 5, one-dimensional momentum and impulse. One of the most important concepts or ideas in physics is the idea of momentum. Newton first used this concept when he phrased his second law of motion. Now, we've told you that his second law of motion is F equals ma. He really didn't write it that way. He rewrote it in terms of momentum. He was much more interested in momentum than just mass and acceleration. He called the product of mass and velocity the quantity of motion. He said if you have a heavy object going fast, the faster it's going, the heavier it is, the more oomph, he didn't use that word, the more motion quantity it had. I kind of think of it as the more damage it would do if it hit something. This product has come to be known as momentum. It's the amount of motion an object has. What makes momentum so important is the fact that, like energy, momentum is also conserved. That means, Megan, in a closed system, as long as you're not having any external sources, any outside sources, the amount of momentum beforehand has to equal the amount of momentum afterwards. Except momentum is a vector, which means the math's going to get a bit trickier. So here is the conserved quantity. In an isolated system, a system in which no external sources interfere, the total momentum of the objects in a system will remain constant. This is the law of conservation of momentum. Any moving object has momentum. We use the letter P. We can't use M for momentum. That's taken by mass, Gabby. So because it's a motion product, we use the letter P for product. Momentum is mass times velocity. As an equation, it's mv, and both P and V have vectors. Momentum gets its direction from the direction of the velocity of the object you're looking at. What are the units for momentum? What do I measure mass in? What do I measure velocity in? The units are kilogram meters per second. Jaron, you may recall that force was kilogram meters per second squared. It was mass times acceleration. And about 100 years ago, physicists said, let's call that a Newton, because it's less writing. They haven't yet renamed this unit. There is a movement afoot to rename this unit an Einstein. It may happen in your lifetime, but right now it's still a kilogram meter per second. Einstein doesn't have a unit named after him, and he was a biggie. We think maybe we should. So, it's a vector quantity, and the direction of the momentum vector is the same as the velocity vector. That means when you add momentums, or momenta, which is actually the plural of momentums, we're going to be doing lots of drawings tip to tail. Tip to tail. Lots of them. You can rewrite Newton's second law in terms of momentum. You may recall that F equals ma. The definition of acceleration, well, first of all, let me rewrite m. Acceleration was a change in velocity. So Tyler, I can rewrite this as change in velocity over change in time. And what's change in anything? I can rewrite this as mass V final minus V initial over time. I can times by t. I can write this as force times time equals m V final minus V initial, or force times time equals m change in velocity. This is one of the equations that's on your formula sheet. Although I think they have a delta in front of the t. I think it's F delta t equals m delta v, because that way it looks pretty and symmetrical. Okay. Newton's second law can be stated in words in terms of momentum as follows. An unbalanced net force, ta-da, acting on a body changes its motion so that the rate of change of momentum is equal to the unbalanced force. What's the rate of change in momentum? Mass times velocity divided by time. We said when we looked at power, whenever you want to look at the rate of change of something, you divide it by time. The harder you push, the faster something's momentum changes. Impulse. If we rearrange the equation for net force by multiplying by delta t, we get this lovely equation here. This is your impulse equation. Impulse is defined as change in momentum. They are interchangeable, at least for Physics 12. Dorothy, when I say impulse, you know what I really mean? Change in momentum. When I say change in momentum, you know what I really mean? Yep. Oh, and what's change in anything? That, because it drives me crazy this year, there are questions either on the test or in the homework or on the quiz where I say, find the impulse. Kids go, where if they realized impulse is change in momentum and they would know to go final minus initial, then they're home free. They just can't make that leap. You can change the momentum in several ways. First of all, you can have a large force acting for a short time, or a short force acting for a long time. The worst ones are a large force acting for a long time. Units for momentum and impulse. Momentum has measuring units, which are mass times velocity, kilogram meters per second. Impulse has the units of force times time, which are Newton seconds. However, Newton's measure force. Force was what times what? Come on. Force was what times what? MA. It was kilogram meters per second squared. That's Newtons times seconds still, because there was a seconds in my little expression here. And Gabby, can you see that you actually find out that Newton seconds is the same as kilogram meters per second? It is also equivalent units for momentum. They're interchangeable. If I'm going to be really fussy, Megan, technically when you're using this one, you should say Newton seconds. When you're using this one, you should say kilogram meters per second. I'm not going to be that fussy. I probably will be when I'm writing them, when I'm answering questions, but if you use one or the other, I don't care. The law of conservation of momentum. The total momentum of an isolated system of objects will remain constant. We're not going to write it that way. Okay? We're going to generally start, don't turn the page yet, I left some room here for a reason. We're going to generally start out any momentum question as follows. Now, what the heck does that mean? Does anybody know what this funky little zigzaggy capital E means? Okay, the sum of, or the total initial momentum has to equal the total final momentum. You may notice when I teach, I'm fairly big on giving you an approach to start out a type of question and then go from there. For example, for forces, what did we do for label the diagram, free body diagram. For distance and a defect, list the data. You know what? For momentum, I always start out writing this. And how do I recognize a momentum question? It has a collision or an explosion. Let me say that again. It has a collision or an explosion. If it's got a jeune, I almost do this without thinking. Now, it may end up being something like this. The momentum of object 1 initial plus the momentum of object 2 initial equals the momentum of object 1 final plus the momentum of object 2 final. That would be true if you had 2 objects, and we're mostly going to limit ourselves to 2 objects this year. We will go to 3 objects a couple of times. The objects may end up sticking together, in which case I wouldn't have these 2 separate. I would have these 2 stuck together as one. Or they may have been stuck together and then split apart, in which case I'd write those 2. So my generic equation, Gabby, that always works is this first one. The sum of all the initial momentum equals the sum of all the final momentum. On a written question, if it's a momentum question out of 7 and you write that, that gets you 1 free mark. Example 4. Here we have a big truck and a small car, and they're going to collide. Hey, that's a collision. The big truck is 2,400 kilograms. It was traveling at 10 meters per second. The small truck is 24 meters per second, and it's 1,000 kilograms. Now, it says this: if conditions are such that the car and truck end up at rest after the collision, how can we say that momentum has not been lost for the system? Let's do a little before, after. Recall, momentum is mass times velocity. Chelsea, after the collision, how fast is the big truck traveling? It's meant to be really obvious. Yeah, no. Look at the picture. After the collision, how fast is the big... Chelsea, how fast is the big truck traveling? 0. How fast is the car traveling? 0. So if momentum is mass times, listen close, velocity, and they both have a velocity of 0, what's my momentum after the collision? 0. You know what that means? What must my momentum have been before the collision? Too slow. What must my momentum have been before the collision? Has to have been 0. Wait a minute, Mr. Dewick, how can that be? Let's see if we can prove it. So before the collision, we have momentum of the truck plus momentum of the car. Right? Which is going to be mass of the truck, velocity of the truck, plus mass of the car, velocity of the car. Right? What's the mass of the truck? 2,400. What's the velocity of the truck? 10. What's the mass of the car? 1,000. What's the velocity of the car? Not 24. 24 would be the speed. Huh? Negative 24. And believe it or not, when you crunch those fake, carefully crafted numbers that I made up, you do find, Dorothy, though, that it is perfectly possible for you to have two moving objects, yet still have 0 momentum, because momentum is a vector. In fact, that would have to be true in any head-on collision if we ignored any outside forces like friction and things like that. So if this was occurring on ice and 2 objects collided and they came to a dead stop, then you know the momentum before, the net momentum, the total momentum, was 0 before. Why? Because it was 0 afterwards. The law of conservation of momentum can be written in several ways. In English, the total initial momentum equals the total final momentum. As an equation, I generally hop right to that bad boy. And we use conservation of momentum when there is a collision or an explosion. Example 1. A rifle bullet of mass 0.06 kilogram leaves a muzzle with a velocity of 6 times 10 to the second meter per second. If the 3 kilogram rifle is held very loosely, with what velocity will it recoil when the bullet is fired? Is there a jeune? Yeah, an explosion. That's what a rifle is. This looks like a job for momentum. First thing I'm going to do is I'm going to write down the sum of the momentum beforehand equals the sum of the momentum afterwards. Before the explosion, before we pull the trigger, what was moving? Mass 1, mass 2, or both? The rifle, the bullet, or both? Sorry? Sorry? Neither. After the explosion, after we pull the trigger, what's moving? Mass 1, mass 2, or both? We're going to have the momentum of the rifle and the momentum of the bullet. And because these are in a nice straight line, we don't need to go all vectory yet. Today, everything's going to be in a straight line. The most we're going to have to do, Jake, is let to the left be negative and to the right be positive. Next lesson, woo, we'll be getting tricky with it, as much as we do all year long. Momentum is mass times velocity. It's going to be momentum of the rifle, or mass of the rifle, 3. Velocity of the rifle, I don't know. Mass of the bullet, 0.06. Velocity of the bullet, 600. I think I would minus the 0.06 over to the other side and the 600 over to the other side. Right? Because there's a 0 over there. And then how would I get the velocity by itself, Ty? The rifle velocity is going to be negative 0.06 divided by 3. This rifle is going to kick back. Oh, how do I know kick back? I got a negative answer that's telling me it's going to head in the opposite direction of the rifle bullet. Has to. What do you get? 12 meters per second? Now, whoever's holding the rifle will have to give back a ways with it. Lengthen the time that the force is applied for, because change in momentum is also force times change in time. We'll talk about that a bit later. Oh, a negative. Thank you, Dorothy. Negative 12. I should never have listened to Mabad. First mistake. I have an answer. I could have let, like, on this line right here, I could have let the 600, I was envisioning firing a rifle to the right, so I figured the bullet's going to go forward, positive 600. You could have let the bullet's velocity be negative, and you'd get a positive velocity for the rifle. What's going to happen no matter what is you're going to get opposite signs for your velocities. Is that okay? Football. What is the momentum of a 112 kilogram football player running at 4.8 meters per second? Okay. Momentum is mass times velocity. Mass, 112. Velocity, 4.8. This young football player, whoever he is, has a velocity, has a momentum, good gosh, of 538 kilogram meters per second. B. So, if I'm tackling him head on, what impulse must I impart to stop him? What change in momentum must I impart to stop him? Because impulse is another word for change in momentum. Now that's assuming I hit head on. If I hit at an angle, it's tougher. Because I'd have to go components. C. If the tackle is completed in 1.2 seconds, now 1.2 seconds is probably way too long for a tackle, but I was making up numbers. If the tackle is completed in 1.2 seconds, what average force must the tackler have exerted? Okay, now we have a time and a force. You know what, Alicia? I'm going to use the other definition of impulse. I'm going to realize that impulse equals impulse. They want me to find the force. That's going to be the change in momentum divided by the change in time. It's going to be negative 538 divided by 1.2. I'll use the 537.6, so negative that answer divided by 1.2. And I have to exert an average force of negative 448 newtons. What's the significance of the negative? It has to be in the opposite direction that the player has been traveling. Jason's dream has come true. He's an astronaut. I never told you that was my secret dream. I just knew. So Jason is doing a spacewalk outside the space shuttle, but he's not clipped on with a cable. He's using the fancy schmancy rocket pack, and suddenly his rocket pack quits on him. He's stranded in space with nothing but a $50,000 camera in his hands. What can he do to get back to the shuttle? Jason, what? Throw the camera in the opposite direction of the shuttle. Why? Right now, what's the momentum between you and the camera combined? 0. So afterwards, what must the momentum be? Still 0. So if I give the camera a positive momentum away from me, I must pick up a negative momentum in the opposite direction. Momentum is what times what? Mass times velocity. Will your mass change? Then it has to be your velocity. Now, because you have such a big mass compared to the camera, your velocities won't be equivalent, but it'll be enough. You'll drift slowly, 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 and you'll make your way back. Pardon me? You'd lose the camera. If you're bored sometime, do research on the amount of space debris that's out there. It's becoming a problem now because all of that is moving at an incredible speed. Even a small object like a paint fleck has enough kinetic energy to punch a hole through the space shuttle or through the space station. And so now we're finally going back up there to start cleaning up our mess. I think Switzerland, there's all sorts of, one of the X Prizes is looking at a way to clean up outer space because probably in your lifetimes, satellite getting destroyed will become more and more frequently be happening because there's so much garbage up there. I know in 2009, 2 satellites collided, and that gave something like 40,000 more debris pieces up there, like there wasn't enough already. There is, strangely enough, 1 astronaut's glove, and you can Google and find out how the heck an astronaut long glove, and say, what? Yeah, a little bit of a crisis there. So, push camera away from shuttle. If it was not, pardon me?
Would you throw the rocket pack that wasn't working?
Wouldn't you just throw the... Now, that's a great point. I suspect, first of all, they're strapped on you, and I have a feeling even if you could undo the straps, think about the position you're in. How much momentum could you give that rocket pack away from you if you're in a bulky spacesuit? I suspect it's much easier to do a chest pass than it is to somehow... Now, you could possibly maneuver it in front of you, but I suspect if you maneuvered it in front of you, as soon as you pulled it this way, we haven't talked about circular momentum, but circular momentum is also conserved. So by you wanting to exert a force this way, you would start to spin in the opposite direction. Now you'd be spinning. I think it's easier to go with the camera. Astronaut will slowly drift towards space shuttle. By the way, none of you, the obvious solution, you'd radio your teammates, which is why you don't go in outer space alone, and one of them would come out with a second rocket pack, pick you up, and you wouldn't lose any equipment. But that's the... Or he would come out with a cable just to be really, really safe. Haul you in. But this is another way to explain how rocket engines work in outer space. You see, a rocket engine expels gas, mass. And if it expels gas, mass, backwards, and your initial momentum is zero, that has to mean that the object that's left behind, because it's not losing mass, it must be somehow changing forwards. It must have a momentum forwards. A rocket engine is a controlled explosion, a great example of conservation of momentum. A rocket expels 1.2 times 10 to the 3 kilograms of gas each second. And the gas leaves the rocket with a speed of 5 times 10 to the 4th meters per second. Will the thrust produced by a rocket be sufficient to lift it if the force of gravity on the rocket is 5 times 10 to the 7th, 5.8 times 10 to the 7th? Ooh. I'm seeing more than one force. I'm seeing thrust force, see it? I'm seeing gravity force, see it? This looks like a job for a free body diagram. What are the forces acting on this object? Get the obvious ones. And thrust. Who's winning? We hope. Basically, we want this. We need that. We need the thrust to be bigger than gravity. If the thrust is bigger than gravity, because this question isn't asking how fast is it lifting, it's saying, will it be sufficient? Okay. How can I figure out the thrust force? I got the gravity force, 5.8 times 10 to the 7th. How can I figure out the thrust force? Well, I see a force and a time. How about we go... impulse equals impulse. That's the rocket force. In fact, I think, Jaron, this force here is the thrust force. How would I get it by itself? Yep. I'm going to get this. An expression for the rocket thrust from the engine is going to be m change in velocity over change in time. How much time is mentioned in this question? You have to look really carefully to spot it. 1 second. How much mass in 1 second? Now, change in velocity is final minus initial. I'm pretty sure the initial is 0 before you turn the engine on, yes? What's the final? 5 times 10 to the 4th. Will that be bigger than gravity? Let's find out. If it is, we have liftoff. If it's not, we're in trouble. It's really just going to end up being 1.2 times 10 to the 3rd times 5 times 10 to the 4th, because dividing by 1 minusing 0 isn't going to make a change. And I get 1, 2, 3, 4, 5, 6, 7. Yep. I got 0.2 times 10 to the 7th, or 2 times 10 to the 6th. Extra newtons left over for acceleration. In fact, I could even figure out the acceleration if I really wanted to. Woohoo! Collisions. A 3.2 kilogram cart traveling 1.2 meters per second collides with a stationary 1.8 kilogram cart, and the two carts stick together. What's their common velocity after the collision? Did I say collision? This is a job for momentum. By the way, Mr. Duick, how come here you didn't go the sum of all momentum? You'll notice here I saw time and force. I figured I'd probably be ending up with the impulse equation. But if it's a straight collision, the sum of all the initial momentum has to equal the sum of all the final momentum. Before the collision, what's moving? Cart 1, cart 2, or both? Cart 1, so it's going to be the momentum of the first object initially. The second object, Alicia, since it's stationary, has a speed of 0, therefore a momentum of 0. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Momentum of all final. Or momentum of both final, whatever you want to write. There's our equation. We're going to have this. Mass 1, V1 initial, there's my initial momentum, equals, they stick together, so it's going to be mass 1 and mass 2, V final. Are these in a nice straight line? So I don't need to go drawing vectors tip to tail. I can just solve this. How would I get V final by itself? V final is going to be M1 V1 initial divided by M1 and M2. It's going to be 3.2 times 1.2 divided by 3.2 plus 1.8. And I get, they're going to roll off at 0.768. Someone want to double check me? I think that's right, though. Positive or negative? Positive. Oh, they're going to roll forwards. Okay. Example 6. A 6 times 10 to the 3rd kilogram railway car is coasting along the track at 7 meters per second. Suddenly, a 2 times 10 to the 3rd kilogram load of coal is dumped into the car. What's its new velocity? It's going to slow down because the mass has changed, but I'm not a big fan of this question because I'm going to nuke it. I don't like the fact that we have a mass being added vertically when the car is traveling forwards, and some people always, well, wouldn't there be some momentum from the okay, yeah, let's do this one. Example 7. A 1.2 times 10 to the third kilogram car traveling 33 meters per second collides head-on with a 1.8 times 10 to the third kilogram car traveling 22 meters per second in the opposite direction. You know what? That's an important phrase. I'll underline that, in the opposite direction. If the cars stick together, what's the velocity of the wreckage immediately after impact? Ben, is there a collision? This was like a job for momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what's moving? Mass 1, mass 2, or both? So I'm going to have mass 1 initial, momentum 1 initial, momentum 2 initial. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? If they're separate, I'd have mass 1 final, or momentum 1 final, momentum 2 final. But they're stuck together, so let's go momentum, both, or all, final. Momentum is mass times velocity. So it's going to be mass 1, v1 initial, plus mass 2, v2 initial, and that equals mass 1 plus mass 2, v final. Going to be mass 1, 1.2 times 10 to the third, v1 initial, 33, plus mass 2, 1.8 times 10 to the third, v2 initial, don't say 22 because it's not. Sorry? Yeah, it's absolutely negative 22 because it's a velocity now, not a speed. That equals, you know what? V final, how would I get the V final by itself? I think I would divide by both masses, yes? So I'm going to do that right now. Divided by 1.2 times 10 to the 3 plus 1.8 times 10 to the 3. I'm curious, in this collision with a smaller car going faster and a bigger car going slower, who wins? Will it end up with a negative answer, in which case they move backwards in the direction of the heavier car? Or will it end up with a positive answer, in which case they're moving forwards in the direction of the smaller car? Or will we fluke and end up at 0, in which case, you know, I cooked the numbers. I can't remember what the answer is for this one. Can we solve it already?
I think it's 0.
You think it's 0? Is it? Is it 0? Oh, geez. So this would be the classic Hollywood head-on collision where two cars bang into each other and they both stop right in front of the camera because they don't want to have to move the camera. Right? Example 8. Hitting a baseball, that's a collision. What impulse must be imparted to a 145-gram baseball to change its velocity from 48 meters per second south to 50 meters per second north? What are they asking me to find in this question, Terry?
Change in velocity.
Gotta be fussy. No. First of all, what are they asking me to find? A word that begins with the letter I.
Impulse.
Impulse. What's another word for impulse? Not change in velocity.
Change
momentum, which is hugely different, hugely different. So I'm going to start saying, I got two equations for impulse. I got change in momentum can be force, change in time. Do you see a force or a change in time mentioned in part A at all? Well, my other equation for change in momentum or impulse is mass change in velocity. Do you see a change in velocity mentioned in that question at all? Okay, we're going to use that approach. Did I just, Megan, show you how you can figure out which approach you use? Yeah. Okay. And then sometimes you'll use both at the same time. Mass, 0.145. What's change in anything? What's the final velocity? 50 minus. What's the initial velocity? Not 40. Why do I have to call it negative? Okay. Or you could have let south be positive and north be negative, but we're used to letting up be positive, so I went with that. .145 times 50 minus negative 40. And I get a change in momentum of 13.05 or 13.1 kilogram meters per second. Chelsea, is that answer positive or negative? That means that the change in momentum was in the northern direction, which makes sense because if I have a ball heading south, I have to first of all apply a northern force to bring it to a stop. Then I got to apply more northern force to get it to go further north. Oh, okay. Speaking of force, B. Now they want me to find force. Well, I think now I'm going to use my second definition for impulse, which is F delta T. Alicia, how would I get the force by itself, kiddo? Darn right I would. Oh, I just figured out the impulse. 13.1 divided by 1 millisecond. 1 times 10 to the negative. What the heck was milli? It's on your form. You got your formula sheet there? I see a yellow. It's on there somewhere. I think it's 10 to the negative 3. Yeah. 13.1 divided by 13,100 newtons. Is that a big force? It's a baseball bat. You wouldn't want to get hit by it. Oh, I typed it right. Thank you. 13,100 newtons. Mr. Duick, would I be marked wrong if I had called this one positive and that one negative and got a negative answer there? No, I would give you full marks as long as you were, and you'd get a negative answer there. Totally good. Totally fine. As long as you're consistent, Megan, throughout the whole question. A 2 times 10 to the third kilogram car traveling 15 meters per second rear-ends another car of mass 1 times 10 to the third kilograms. The second car was initially moving at 6 meters per second in the same direction. What is their common velocity after the collision if the cars locked together during the impact? Think we can handle that? Yeah? Well, then let's skip it. It's a nice question. But you guys are zoning out. I want to make sure I get through the whole lesson. Example 10. 2 eggs are dropped from a height h. One hits the floor and breaks. The second one falls in a pail of water and survives. What's the main reason that the second egg survives? Pardon me? Time is longer? Jason says time is longer. What does he mean by that? You know what? Let's make a little, in our argument here. For both eggs, What's the initial velocity? For both eggs, will you agree with me that the impact velocity is the same because they're being dropped from the same height? Is that okay? The mass is the same for both eggs. What that means is if your initial velocity, your final velocity, and your mass are all the same, it means they both go through the same change in momentum. So what can I do, Jason? I can't change the mass. I can't change the final velocity. What can I do? Give me your argument again. So you're saying that we also know that change in momentum is equal to that? As t increases, if this number gets bigger, what happens to force? F decreases. Oh, yep.
How come both the vests don't lengthen the impact time at all?
They do lengthen the impact time somewhat, but the fibers are cross-woven in such a way that they take the kinetic energy, which is a scalar, and they spread that energy out over a larger area. And by spreading the energy out over a larger area, what they're letting your body do is, freeze the screen, freeze the lesson again. It's a good question. We'll come back to it. So back here, after my little bulletproof vest rant, example 11. If we look at a graph of force versus time for the egg hitting the floor, it will look as follows. What's on the y-axis? Force. What's on the x-axis? What do you think the area of this graph means? Now, I gave you some graph analysis tools last unit. I said, you know what? If it's an area, what do you do with the quantities? Times. So you're saying if I was trying to figure out what the heck that area was, I would go like that, and then I might think to myself, hey, I've seen an equation that has force times time in it. We've been looking at it quite recently. What is the area underneath this graph? I don't need to tell you. You can derive it. What is it? Impulse. Turns out the area under a force versus time graph is impulse. Okay. Which of the following graphs, A, B, or C, would best represent the force-time graph for the egg hitting the water? The egg on floor graph is shown as a dashed line for comparison purposes. I don't think that dashed line appeared anymore on yours, did it? Do you guys have a little dashed line? Like, you don't have that there? Okay, so you have to use your imagination based on this graph here. Shrink it down. I think I told you, my friend who typed this up in Word 95 for Mac. So the graphics are slowly dying. I'm going to have to replace them as the years go on. Otherwise, it's good handouts. Jason, why C? Okay, first of all, do you remember I did say they have the same change in momentum, which means they should have the same area if I'm eyeballing it. My issue with A is, looks like the amount of time hasn't changed. Somehow you've lowered the force, but you haven't changed the amount of time. I think you've violated the laws of physics to do that. My issue with B is, okay, you've lowered some of the force. I think if I kind of divide this in half and add up that area, I think I'm getting a bigger area than dividing that one in half and adding it up. C? Yeah, I'd probably go with C. C. You know what? For me to be really accurate, I need to give you some kind of a scale. So you could go base times height divided by 2 and do the quick math, because it's triangles. Okay. It says explain your answer using appropriate physics concepts. We just did. What's your homework? Number 1. 2 is good. 3 is good. I think I like number 3. I think I do. 4 is good. 5 is good. So far I've assigned 1, 2, 3, 4, 5. Jet plane at rest. Sure. 6 is good. 7 is a work versus time graph, or force versus time graph. That's a work and energy question, which is nerdily cool, but we already did our test. Yeah. Sure, 12. Couple of videos.